This section, 3.1, dealing with derivatives. We spent a little bit of time last year talking about derivatives, how they work, what they are. This is a little bit of the foundation of some of that idea. And hopefully a lot of what's in here should look familiar to you, as we touched on a little bit last year. What we're supposed to be able to do is find a derivative and apply it to a variety of different kinds of problems. The thing that you're going to find in calculus is that these ideas can be applied in just so many different areas. And that's kind of the strength and the value of what calculus is and has been to develop a variety of different scientific discoveries. So last year I gave you this equation, and we called it the limit of the difference quotient. And the idea is it's a quotient, it's a division problem. It's also a subtraction problem, so it's a difference. So it's the limit as h approaches 0 of f of x plus h minus f of x all over h. That's how you read that. But it has a name, and what that is the derivative. The derivative is the limit of the difference quotient. So when you see this notation in something, understand that to mean that they're finding the derivative. So what does that mean? Well, and some other notation. You'll see this f with the little dash up here. That's not a 1. It's like an apostrophe almost, but that's a prime symbol. So f prime of x, or the derivative of f of x. And again, not a 1, so you have to be careful to separate that that's not an exponent in that way. So here was the idea, if you remember, we talked about last year. If I'm interested in what the slope of this red line is, well, typically to find slope, you have to have 2 points, and then you do the difference in the y values over the difference in the x values. Well, I don't have 2 points, so what I do is I scoot over a little bit. I scoot over h units. And when I scoot over h units, this distance then from here to here is h units, which makes the coordinates of this point a plus h. So now I have a point at a, and I have a point up here at a plus h. And then when I use those 2 points, I can draw a secant line. Well, the slope of that yellowish line and the slope of the red line are sort of kind of close, but they're not the same. The logic then was that I can find the slope of that yellow line doing the difference in the y values over the difference in the x values. But since I'm not very close, it would seem to make sense to see if we can make h a little bit smaller. And notice what happens. I'm going to back up a slide. I went from a slope like that to a slope like that. The two slopes got a little bit closer. And then that's where the whole premise of the idea of the limit comes from. I want the value of h to approach 0. And when that does, the slope of that line and the slope of this line will become the same. So a variation on the theme of that is this equation, f of x minus f of a over x minus a. You'll see both these equations in this section, and they mean the same thing. The difference here is that the a could represent a specific value. If I knew what x was, I could figure out what a was. I might have a specific value out here. So this, instead of being the function evaluated at a, I'm plugging in a number, and so f of a number, that could be a number in that situation. But the logic is still the same. So look what this says now. Instead of it being this distance being h units, we're talking about the difference from x to a is just the subtraction. So what I want to have happen is I want the x value to approach the a value. And what I'm finding here is the slope of a tangent line again, as that gets smaller and smaller. So again, here's a, this is f of a, here's x, this is f of x. And as these two values get closer and closer and closer to each other, the slope of these tangent lines the secant line gets closer and closer to the slope of the tangent line. So one of the questions that you'll see is use the definition to find a derivative. So to do that, it's a little bit of a lengthy process. We know some shortcuts, but we need to kind of have down this long method as well. Limit of difference quotient. So I'm going to take the function's x squared minus x. Everywhere in that equation I see an x, I'm going to plug in x plus h. So x squared minus x, I plug in x plus h, plug in x plus h. Then you subtract, and that subtraction right there is that subtraction down there. It says subtract the function, so there's the function being subtracted. Limit as h approaches 0, all over 0. If you leave that off over here, I'm going to mark it wrong. So let's see, I take that equation and I did a little foiling here, distribute the negative in here, distribute this negative, and get that. If you do this step correctly, everything that doesn't have an h in it should cancel out. So the x squareds cancel out, the x's cancel out. Everything that's left has an h in it. So again, still limit as h approaches 0, but I'm still not allowed to let h be 0 because it's in the denominator. I notice that everybody in the numerator has an h in it, and so when I factor the h out of the numerator, these h's are going to cancel, and now I'm able to plug in 0 for h, and I get just 2x minus 1. I get it, we could have gotten there with the shortcuts, but this concept, this process, is a kind of an underlying procedure that you need to have in your head. So don't lose it. So again, what a derivative is finding for us is the slope of the tangent line. So if I have some function, and at this point, the slope of the tangent line would be the slope of that black line. Think of that as the instantaneous rate of change. Now, as I mentioned, there's a bunch of different kinds of applications that apply to that, but being able to find the slope of the tangent line, or f prime at A, is a big deal in a variety of areas. If you were to do a business major, you would see, you would probably have to take calculus for business students, and one of the things they would talk about would be the marginal cost or the marginal revenue. And the marginal cost is essentially the slope of the tangent line at a particular point. It's the rate of change at a particular point. Instantaneous rate of change at a particular point. So here's kind of a weird example, but manufacturer produced bolts of fabric fixed with. The cost of producing X yards of this fabric, the cost, is C equals F of X in dollars. So you tell me how many yards you've got, and this equation will tell you the cost of producing that much. So the derivative is the rate of change of. So anytime you see this question, the answer is always going to be the derivative is the rate of change of the, and then you simply fill in the blank. What is the function? Well, the function here is the cost of producing X number of yards. So this question is simply the meaning of the derivative of f of x is the cost, the rate of change of the cost of producing X yards of fabric. So it's the rate at which the cost is changing, not the total cost, the rate at which the cost is changing. What would f prime with 1,000 equal 9 mean in practical terms? The derivative is the rate of change of the, and f prime in this problem is the cost. So the derivative is the rate at which the cost is changing. So the rate at which the cost is changing in this case is 9. Now remember this was in dollars, so that's $9. That doesn't mean it costs you $9 to produce it. That means the cost is changing at a rate of $9 per yard. So in other words, approximately, the next 1 yard of to produce is going to cost you $9. Because whatever it costs you to produce, let me make up a number. Sorry, I don't have to make up a number. I've got 1,000. So the 1,001st yard is going to cost you $9 because the total cost is going to change by $9. So this is the rate at which the cost is changing, and the cost is changing at a rate of 9. So the next one's going to be $9 more. Now that's an approximation because that's at 1,000, not at 1,000. Not at 1,001. So whatever the however the cost is changing, the slope at 1,000 would be 9. The slope at 1,001 would be a little less than 9. So that's an approximation of what the next one will cost. So which would be greater? The rate at which the cost is changing at 50, 500, or 5,000? So there's a couple of interpretations of this. Typically, though, what you find, the reason stores like Sam's Club or Costco, those big stores that tend to sell things in bulk, the reason that they tend to be able to sell things cheaper is that when you buy it in bulk, it's easier to ship and produce and so on. So the rate of production costs typically would get cheaper as you move your way down. So, if you produce just one of something, there's a lot of cost to that because there's a lot of, you have to buy the machinery, you got to rent some space, you got to buy the raw materials, etc. So producing more of something doesn't radically increase your costs, and so typically your costs might be going down to produce. Now, if you think of this as total cost, and again, there's kind of some interpretations about how you look at that, then your total cost is going to go up. You're not going to have less cost to produce more, but have more cost to produce more. So it's kind of how you think about what they mean by f of x equaling c. And so that's kind of the perspective of the book, that producing more can't be cheaper. Now the cost per item would be maybe cheaper, but the cost of producing more is going to keep going up and up and up and up, even though that the rate at which it's going up might be getting less and less and less. For example, the rate of change of 5,000 might only be 6. Instead of it rather than 1,000, it was 9. So that means the rate's still going up, but it's going up more slowly. That's the idea of what's going on here. And the idea of that last problem was to see that the rate of change of something can be applied in a ton of different areas. And as we advance through this, we're going to do rate of change to just a variety of different kinds of problems. And no matter how many different ways I come up with ideas for you in this course, the AP test is probably going to ask you something about a rate of change or something we haven't talked about. And you just got to recognize, oh, this is a rate of change, that's a derivative. We'll get more and more into the next sections how to do the shortcuts. Mostly that's what we'll be doing. But for now, be able to use the limit of the difference quotient and recognize it in a couple of different forms.